Hello there. My name is Noah Bennett, and I want to thank you for being here with me tonight. Before we begin our story, I invite you to take a few quiet moments just for yourself. Find a comfortable position. Let your shoulders soften. Rest your hands wherever they feel most at ease. If you wish, gently close your eyes. It's one I thoroughly enjoyed recording. Just my kind of sleepy story. By the power of imagination, we'll be traveling to space. We're going to accelerate to several thousand times the speed of light until we reach the distant Andromeda Galaxy. Along the way, you'll learn all about our galaxy, the Milky Way, and so much more. We'll look at the possibility of intergalactic travel, the mystery of dark matter, and whether life could exist elsewhere in the universe. Everything is going to be easy to understand, even if you don't know much about physics or astronomy. Just let the sound of my voice guide you. Before we launch into the majesty and grandeur of the universe, let's focus on being present in the here and now. This is something our thinking minds can struggle to do, but our bodies have no option but to be in the present moment. So tune your mind's focus into the body. As you lie in your bed, notice where your body is in contact with the mattress. Feel your muscles softening as you sink deeper into the support of those contact points. How does your body feel? Are you warm and cozy? Are your muscles achy or tired from the day? Or perhaps there's some excess energy lingering around that you want to release. Take a slow, gentle breath in and feel it move through you like a warm stream of light. Let the breath travel into the places inside you that feel tight, tired, or unsettled. As you breathe out, imagine any tension simply melting away, flowing out of the body like mist disappearing into air. Inhale, calm. Exhale, release. With each soft breath, your body grows heavier, quieter, more at ease. Now, notice the gentle support beneath your head, your pillow holding you with quiet care. Let your neck soften, your jaw loosen, your thoughts begin to drift away, like leaves floating on still water. Feel the blanket resting over you, warm, steady, and safe. A soft cocoon wrapping you in peaceful comfort. Here, nothing is required from you. Nothing to fix, nothing to think about. Just rest. Just breathe. Just be. While you listen to our story, know that you can return to this sense of presence by using the breath and your senses in the here and now. But feel free to follow along on our wonderful journey to a distant galaxy, allowing your imagination to picture the awe-inspiring sights. We will soon leave Earth and go further than anyone has ever gone, all the way to Andromeda. This is where our story begins. Our destination is extraordinarily far away, and yet you have probably already seen it. Perhaps on a clear, moonless night in an area with limited light pollution. It is so big that it's sometimes visible to the naked eye, and it appears in the same area of the sky as the constellation of Andromeda, hence the name given to the galaxy. Even though the galaxy is far, far beyond the stars that form the constellation. But first, let's take a look at where our planet is in our galaxy. We are used to thinking about the position of Earth relative to other bodies in the solar system. We think of the Sun at the center, orbited by other planets. But the Sun is just one star among hundreds of billions that orbit around another center, the center of the Milky Way. The Milky Way is shaped like a gigantic flat disk. When bodies orbit around the center, they tend to align on the same plane. This is an effect of gravitational forces that keep them together. But star systems or galaxies are not perfectly flat. The Milky Way is 1,000 light years thick, and it's estimated to be 100,000 light years wide in diameter. So it's about 100 times wider than it is thick. In pictures, galaxies are sometimes portrayed with an oval shape, but this is because they are represented as if seen from the side with an inclination. Viewed from the top, the Milky Way would look circular. Of course, galaxies are not all alike. Some have only tens of millions of stars, while others have hundreds of billions, and their shapes vary too. Among large galaxies, 3 main shapes have been observed. The most common ones, like our own, are spiral galaxies. Their stars are organized on a disk, but they concentrate on arms originating from the center. Most spiral galaxies have a central concentration of stars known as the bulge. This is why the center appears more luminous. The arms of the galaxy also seem very luminous, because they contain a higher concentration of stars, and they're often younger stars which shine brighter. It is believed that these stars are born from nebulas, which are giant clouds of gas and dust. Sometimes parts of nebulas collapse on themselves. The gravitational forces then lead to the accretion of matter, forming a new star. The Milky Way contains various nebulas, and when a star dies after billions of years, it may disintegrate, returning its matter to the nebula. The majority of spiral galaxies also have a bar-like structure that extends from the bulge. The Milky Way has one. Its spiral arms begin at the ends of the bar, but not all galaxies are spiral-shaped. Another type is elliptical galaxies. These ones have an ellipsoidal shape, which is like a sphere that's been slightly flattened. Seen from afar, they look like a smooth and nearly featureless halo of light, with more luminosity in the center, where more stars are concentrated. When these elliptical galaxies were discovered, it was believed that they were younger and that they could later evolve into spiral galaxies. But we now know that this is not the case. In fact, the stars they contain are on average much older than the stars found in spiral galaxies. And finally, there's the third type, irregular galaxies. Irregular galaxies are unique in shape. They do not have the smooth, rounded core of elliptical galaxies, nor the graceful, spiraling arms of spiral galaxies. Instead, they look like drifting clouds of stars scattered across space. Many of these galaxies did not begin this way. Some were once spiral or elliptical, but external forces, such as gravitational pulls from neighboring galaxies or cosmic collisions, twisted and reshaped them over time. On average, irregular galaxies are much smaller, often only a tenth the size of spiral galaxies. Because of their smaller mass, they are more vulnerable to being pulled in, colliding with, and eventually being absorbed by larger galaxies. The study of these galaxies was significantly advanced by the American astronomer Edwin Hubble, the same Hubble for whom the famous Hubble Space Telescope was named. Working in the early 20th century, Hubble revolutionized humanity's understanding of the universe, expanding our knowledge of its structure, its scale, and our place within it. One of his most significant findings was that clouds of dust or gas that were visible from the Earth were in fact galaxies beyond the Milky Way. Hubble started to map visible objects in the sky to differentiate what was part of our galaxy and what was at an extragalactic distance. He also contributed to the discovery that galaxies that were more distant from Earth tended to recede more quickly. This is important because it's a clue that the universe is expanding. It became one of the elements that supported the Big Bang Theory and made it go mainstream. So, where are we inside our spiral-shaped galaxy? The answer is midway between the center and the side. The radius of the Milky Way is 50,000 light-years. We are approximately 25,000 light-years away from the center, and a similar distance from the edge. So, if we exited the galaxy by traveling along the disk at light speed, it would take 25,000 years. This gives us the idea of the size of our galaxy. We are far too small and slow to even imagine reaching the edges of the Milky Way, let alone traveling to another galaxy. Andromeda is 2.5 million light-years from us. So when we look at the sky and see Andromeda, what we're actually seeing are rays of light that the galaxy emitted 2 and 12 million years ago. The fastest spaceships ever built travel at a fraction of the speed of light, much less than 1% of it, in fact. But even if we could reach light speed or close to it, the journey across our galaxy would still be a very long one. As we said before, the diameter of the Milky Way is estimated to be at least 100,000 light-years. So reaching another galaxy just doesn't seem plausible. But if we suppose the technical limitations can be overcome, is it possible to move faster than light from what we understand of physics? Probably not. At least not for human beings made of matter as we know it. According to the theory of relativity, when a body with a mass accelerates close to light speed, its mass increases steeply and becomes infinite, and so does the energy required to move it. Light photons, on the other hand, have no mass. This is how they can travel so fast. The increase in mass when matter accelerates and comes close to light speed has been studied in particle accelerators. In these machines, particles like electrons are propelled. This allows scientists to observe the properties of the electrons when they accelerate or when they collide. In the 1960s, scientists observed that at some point when the electrons accelerated, they needed to provide them with more and more energy to ensure they keep accelerating. And even though the electrons came close to light speed, they could never quite reach it because they got heavier and heavier. Obviously, it's impossible to provide them with the infinite quantity of energy that could move their infinite mass. Our bodies and anything we build are made of the same matter that can be tested in particle accelerators, and they are subject to the same laws and therefore the same limitations. So it seems impossible, or at least implausible, that a human being will ever travel at light speed. Even the fastest man-made vehicles are much slower than light speed. For example, one of the fastest flying objects ever built is a space probe called New Horizons. This probe reached the limits of the solar system a few years ago. It managed it at a speed of 16 kilometers per second, or about 10 meters. 16 kilometers per second is already a speed that defies our imagination. For example, it puts Los Angeles at less than 5 minutes from New York City, and a complete journey around Earth would only take 40 minutes. But this is still very slow in comparison with light speed. Light doesn't need 40 minutes to travel around the Earth. It needs about 1/10 of a second, and it travels almost 20,000 times faster than the New Horizon probe. But even assuming we could build vehicles that are thousands of times faster and that we could come close to light speed, interstellar travel would still take a long time, and intergalactic travel would still be out of reach. But what if there is another way? Perhaps the universe isn't limited to the familiar parts we see. We experience space as three-dimensional because that is how our senses interpret it. Yet Einstein's theory of relativity hints that reality may be far richer and more complex than our perception allows. For decades, scientists, along with Francois Hochfintung, have imagined the existence of hidden pathways within the fabric of space-time. Shortcuts, passages, a way to fold the vastness of the cosmos so that two distant points suddenly lie next to each other. These hypothetical routes are known as wormholes, structures that could connect far-off regions of space and time like tunnels carved through reality itself. If such wormholes could be found, or even created, A spacecraft might not need to travel across the endless distance between stars. It could simply step through the opening and emerge somewhere else almost instantly, as though the universe itself offered a door to another corner of the cosmos. The two ends would connect different parts of space, different universes, or different points in time. But this is completely hypothetical. No wormhole has ever been identified. However, science fiction quickly embraced the concept decades ago because it was a way to explain very long distance travel in a short time. It gave stories a varnish of scientific credibility. This is why the concept of wormholes has become famous even though their existence is far from certain. Still, maybe one day a wormhole will be identified. After all, black holes were also hypothetical for a long time before they were finally observed. Now, let's return to our journey. Imagine that we have left the solar system behind, and we are now in an interstellar void. We're on our way to Alpha Centauri, the star system that's closest to Earth. Alpha Centauri already gives us a glimpse of the diversity of stars and systems in our galaxy. It's only 4 light years from Earth, but unlike our solar system, which has 1 star, the Sun, Alpha Centauri has 3 stars. 2 of them orbit together, forming a binary star. From Earth to the naked eye, they look like a single star that appears in the constellation of Centaurus, hence the name of the system. But they are not alone. There is a 3rd star that is almost invisible from Earth, Alpha Centauri C, or Proxima Centauri. This star is a red dwarf. Red dwarfs are smaller and cooler than sun-like stars. This makes them harder to spot because they don't emit as much light. Red dwarfs are abundant. It's estimated that they represent more than half the stars in the Milky Way. And they can also potentially exist for much longer than other types of stars because they burn through their fuel very slowly. Red dwarfs may be able to burn for trillions of years, as opposed to mere billions of years for more shiny stars. This is a much greater lifespan than the age of the universe, which is estimated at about 14 billion years. At an advanced stage of evolution, Proxima Centauri orbits around the 2 bigger stars. Little is known about the system. However, planets have been discovered in it, including one called Proxima Centauri b, which orbits around the red dwarf. This planet is the closest exoplanet to Earth that has been discovered so far. Exoplanet simply means planet outside of the solar system. This one, Proxima Centauri b, is in the so-called habitable region around its star. Habitable region means that in theory, the planet could have conditions that are compatible with the existence of organic life. Now that we've reached Proxima Centauri, we're going to accelerate even further and travel thousands of light years in mere minutes to reach the edge of the Milky Way. As we start to see it from the outside, we may notice that the entire galaxy is spinning around its center. We will see later when we arrive at Andromeda what lies in the center of a galaxy. It may all look very slow because of the distances, but star systems orbit around the center at high velocities. For example, the Sun and the Earth travel at 230 kilometers per second relative to the center of the Milky Way. However, the Sun's orbit around the center of the Milky Way is so large that it takes more than 200 million years to complete a revolution. This period of time is called the galactic year or cosmic year, and it represents entire eras for our planet. Humanity has been around for only a small fraction of a cosmic year. Earlier, we mentioned that Andromeda was the closest galaxy to the Milky Way, but this may not be exactly true. It is the closest large spiral galaxy, but there are many other smaller galaxies in the proximity of the Milky Way. One of them is the Canis Major dwarf galaxy. It's also known as the Canis Major over density because its status as a galaxy is disputed. It's located in the same part of the sky as the constellation Canis Major, which can be seen from Earth. The dwarf galaxy contains roughly 1 billion stars. That's not much compared with the Milky Way, which has at least 400 billion stars. The Canis Major galaxy seems to be in the process of being torn apart and absorbed by the Milky Way. Maybe it came too close. It appears to be losing stars to the gravitational pull of our galaxy, and it forms a trail of stars around the Milky Way. but it isn't clear whether it is or was a distinct galaxy, or just a part of the Milky Way's halo of stars. In any case, there's a theory that galaxies may grow in size over time by absorbing smaller neighbors. Now, let's leave the Milky Way galaxy behind and accelerate again to reach Andromeda in a matter of minutes rather than millions of years. We are now in the vast intergalactic void. It is almost an absolute vacuum, but it's not completely empty. On average, estimates point to around 1 atom of hydrogen per meter. It's difficult to study intergalactic space because visually it sends us next to nothing. From Earth, we can only directly see objects that emit or reflect light, such as stars. But even when we cannot see something, we can still learn about it. As the light of distant galaxies travels across the universe, it passes through the vast medium between them. By studying how that light changes on its journey, we can infer what lies in the dark. For instance, we know there are huge clouds of gas scattered between galaxies because part of the starlight gets absorbed as it moves through intergalactic space. The light arrives dimmed, marked, or stamped with the signature of the matter it passed through, like a whisper of what exists in the void. And there are stars drifting out there as well, stars without a galaxy of their own. The Hubble Space Telescope has seen them, lonely stars shining in the space between galaxies. They are called intergalactic stars, or stellar outcasts. Though they make up only a tiny fraction of all stars, hundreds of these wanderers have already been identified. They likely once belonged to galaxies, but were torn away during galactic collisions or gravitational encounters, flung into the vast darkness, traveling alone through the deep and silent sea of space. Let's look at the galaxy ahead of us. Now we can see the spiral of Andromeda growing bigger every minute with its arms spinning around the center. The observation of Andromeda and other galaxies has led to one of the most fascinating hypotheses in astrophysics, the supposed existence of dark matter. It all started in the 1930s. By then, the laws of gravitation were already known, the laws that we think determine the movement of all bodies in the universe when they have a mass and how these bodies interact. This was already well understood, but a number of abnormalities were detected. In particular, galaxies that seem to travel faster than they should, or not exactly in the right direction. Because of the limited technical means of the time, this apparent abnormality was left unexplained for decades. The ghost force that seemed to drive the galaxies in the cosmos remained mysterious. But one hypothesis came from an astronomer called Fritz Zwicky. When he measured the visible mass of the galaxies, he realized it was too small. To explain the movement of the galaxies, the true mass had to be much heavier. So that meant there had to be additional matter that wasn't visible. And it was this invisible matter that kept galaxies bound together and explained their speed and motion. Zwicky called the invisible matter dark matter. But then there was no immediate follow-up to his work until the 1970s, and in particular, until the works of another astronomer, Vera Rubin. She observed the movement of the stars spinning around the center of their galaxies, and she noted that stars that were far from the galactic center were moving much faster than they should. According to the laws of gravitation, the speed of a body orbiting another object depends on the mass of the central object and the distance between them. This is why, in the solar system, for example, planets that are closer to the sun travel faster than planets that are far away. Their speeds range from 44 kilometers per second for Mercury, the closest planet to the sun, to 5 kilometers per second for Neptune. Earth is in between, moving at 30 kilometers per second. If we apply the same logic to a galaxy, the stars that are closer to the galactic center should also travel much faster than stars that are far from it. But they don't. Stars that are 10 times further away from the galactic center in a galaxy like Andromeda, for example, travel as fast as stars that are much closer. This can't be explained by gravitation, unless there is actually more matter than previously thought. Rubin worked on the hypothesis that a cloud of invisible matter existed around the galaxy. This would explain how they moved relative to one another, and it would also explain the motion and speed of the stars that belong to the galaxies. But the problem is, a lot of this invisible or dark matter is necessary to explain the movement of stars. For example, in the Milky Way, it would have to be close to 90% of the total mass of the galaxy. In other words, 90% of the matter contained in our own galaxy would be invisible and unknown. This is not easy to believe, and since Vera Rubin's hypothesis, there's a question that's been keeping astrophysicists busy. What is this mysterious dark matter? There are three possible explanations. One is that dark matter is mainly objects that are known to us, but they're hard to detect because they emit very little light. They are similar to black holes, gas clouds, or red dwarfs. We know these bodies exist, and some have been detected. But even assuming that there are many, many more, the sum of their masses is still far from sufficient to explain the effect of dark matter. Too much mass is missing. So here's a second explanation.
There are particles out there that we don't know of and have never observed because they don't interact with light. What could these mysterious particles be? Well, we don't know. Despite attempts to detect or even create them in particle accelerators, nothing has been found so far. That leaves us with the third explanation. It's that our equations are incorrect and that we need a new theory of gravitation. To complicate things further, various puzzling observations have been made. For example, a galaxy called Dragonfly 44 would have to be made of 99% dark matter to explain its trajectory, and other galaxies would be almost entirely devoid of dark matter. This means that the distribution of this matter would be extremely uneven. At this stage, astrophysicists have had to conclude that either close to 80% of matter in the universe is unknown, or that the laws of gravitation are not accurate. Maybe in the future an explanation of this mystery will emerge, but in the meantime, it reminds us of just how little we know about the universe. We are now in the immediate vicinity of Andromeda. It looks a lot like the Milky Way because it has a spiral shape, but it's larger. Its diameter is twice that of our galaxy. However, the mass of Andromeda is similar to that of the Milky Way, at about 1 trillion solar masses. That's equivalent to 1 trillion times the mass of the Sun. And like the Milky Way, Andromeda has its own system of satellite galaxies. Andromeda is thought to have been formed 10 billion years ago. That would be 3 to 4 billion years after the Big Bang. The galaxy may have been formed by the collision of smaller galaxies. In its first billion years, Andromeda was probably very active with a high rate of star formation. But over the past 2 billion years, it is thought that the formation of new stars throughout this galaxy has almost stopped. The youngest stars have all come from mergers with its satellite galaxies. Like the Milky Way, Andromeda has hundreds of billions of star systems and hundreds of billions of planets too. In the 20th century, we realized that the universe was much, much bigger than we thought before, or at least that it contained more objects. Another breakthrough was the understanding of organic life and the physical and chemical processes that led to its appearance. That brings us to an intriguing possibility. The same conditions that have led to the appearance of life on Earth could also exist in other parts of the universe. After all, the laws of chemistry are the same for other bodies in space,
and the molecules that combine to create organic life are relatively abundant in the universe. The probability of it happening on a particular planet or satellite is very low, but when you multiply that probability by hundreds of billions for the number of planets in a galaxy, and then by billions more for the number of galaxies, you can conclude that the existence of life in other parts of the universe is a near certainty. In the past, life may have existed close to us in the solar system, on the moons of Jupiter, or even on Mars. We also know that the universe was already 10 billion years old when the first traces of life appeared on Earth. So, let's say that life can appear in multiple parts of the universe and evolve like it did for us, into conscious beings that can travel away from their planet of origin or send information like radio waves. In that case, it's strange that nothing has been detected yet. How come they haven't found us? There seems to be a contradiction between the absence of signs of extraterrestrial civilizations and the high probability that they exist.
This contradiction is called the Fermi paradox, after the physicist Enrico Fermi. It's true that it would take a long time to travel across the entire Milky Way, maybe millions of years. But millions of years is not much. Consider that the age of most stars and planets in the galaxy is several billion years. So, we should have found or detected probes or at least signs of intelligent life that can travel faster, like radio waves. This was something Enrico Fermi pointed out in the 1950s, but even earlier in the 1930s it was mentioned by the Russian scientist Konstantin Shklovsky. He wondered, how is it possible that the existence of intelligent life is nowhere to be found? And he proposed one of numerous explanations to this paradox, something called the zoo hypothesis. The hypothesis speculates that extraterrestrial life intentionally refrains from contacting Earth and humans. Perhaps it's because they are not interested, or maybe they want to allow for natural evolution, avoiding contamination. Either way, they could be observing us like visitors, watching animals at a zoo. Another possible explanation is called the rare earth hypothesis. It points out that the set of circumstances that led to the appearance of life and then the evolution of biological complexity are very rare or even completely unique to Earth. The planet needs to be in a habitable zone of a star system and protected from asteroid collisions. Then there's the transition from unicellular life to more complex organisms on Earth. This took hundreds of millions of years, and it may be a very unlikely event. If we follow the rare Earth hypothesis, it makes sense that there are no signs of extraterrestrial life. It doesn't exist. Then again, perhaps it depends on what we mean by life. Life on Earth has existed for about 4 billion years. However, what we call intelligent life has been around for only 3 million years. We define intelligence based on our own genus, Homo, because this is what we know. But consider the fact that human beings have been able to send radio waves and spacecrafts into space. No other species that we know of has ever done that in almost 4 billion years. So this tells us that even after the appearance of life, it may take billions of years before intelligence appears. In the case of Earth, 4 billion years is long enough in comparison with the universe, which is 14 billion years old. So even if life is abundant in the universe, intelligent life able to exit its planet of origin is something truly exceptional. And that would explain why no trace of extraterrestrial intelligence can be found. There are other explanations too, which are a bit gluier. One is that it would be in the nature of intelligent life to destroy itself,
long before it can establish contact. Or perhaps there are periodic extinction events on other planets, which prevent intelligent beings from moving, traveling, or making contact. They go extinct before they have time to do so. Alternatively, if we accept that other intelligent civilizations exist, maybe they are too far apart in space or time. There might only be a few of these civilizations in a particular galaxy. Perhaps they just haven't had enough time to meet yet. Following the same logic, consider that radio emissions by human beings on Earth are relatively recent. The first radio wave emission was in 1895, and even though radio waves travel fast, they have traversed a tiny fraction of the Milky Way. They have reached only a few hundred star systems at this point, when there are hundreds of billions. Another explanation is that the signs of intelligent life are there, but we miss them. Perhaps we are not listening properly. For example, extraterrestrials may transmit signals that have a very high or very low data rate, or they may employ frequencies we consider unconventional. This would make their transmissions indistinguishable from background noise. And here's another idea. Elsewhere, perhaps intelligent life has evolved differently. More advanced beings may have transcended their physical forms and moved to virtual environments, which have become their universe. In that case, perhaps these beings are no longer interested in exploring the physical universe we live in. Space exploration has become meaningless to them. Finally, let's consider this. Maybe the perception that life is meant to expand and colonize is just a cultural feature of our species, something that comes from our minds and our experience of life. Other civilizations may have no interest in this. Perhaps they prefer to stay on their native planets, and they don't even think about leaving or exploring the rest of the universe.
These are just some of the speculations that attempt to explain the Fermi paradox. There are more, but we leave it there for now. It's time to return to our journey. Let's take another look at Andromeda, focusing on its center. Like the Milky Way, Andromeda has a bulge, a concentration of stars that look more luminous. Since the 1990s, the Hubble telescope has sent better and better images of this galactic nucleus. It contains millions of stars and a massive black hole at the very center. The Milky Way also has a supermassive black hole at its center. One day, in more than 4 billion years, Andromeda is expected to collide with our galaxy, and the two black holes may merge. We don't know exactly how things will unfold, but it will be yet another transformation in an ever-changing universe. We are now approaching the end of our galactic journey. It is time to start the return trip to Earth and to fall asleep when you are ready. So, take a deep breath in and back out. Allow yourself to drift off.